Alright, welcome to Module 3.6. We're going to look specifically at neutralisation reactions today. So neutralisation reactions are reactions that occur between an acid and a base. So before we get into those reactions specifically, we're actually going to take a step back and make sure we know what an acid and a base is. And in 1887, Svante Arrhenius was sort of the first person to really come up with a way of actually defining what we mean by acids and what we mean by bases. What he looked at is he saw that when you put those molecules into water, you put an acid into water, you put a base into water, they would sometimes break down and release different things. So acids would break down and release an H plus ion, just called a hydrogen ion, and others would release an OH ion, which we call a hydroxide ion, and those were the bases. So Arrhenius, basically, that was how he defined acids and bases. Acids were molecules that when you put them into water, they release the H plus ion, and bases were ones that would release the OH ion. Now, this is all fine and dandy until we come across a very well-known base called ammonia. Ammonia has the chemical formula NH3. There's no oxygen in it. So how does it act as a base when it can't release an OH ion because it doesn't have the oxygen there to release? So along come a couple of other people, Bronsted and Lowry, and they explain the definition to basically acids are H plus, or sometimes we actually call this proton donators, and bases are proton or H plus acceptors. I actually got a little bit of a video here going over what this is and going into a bit more detail.
The Arrhenius theory of acids and bases defines an acid as a substance that releases protons in solution, and a base as a substance that releases hydroxide ions in solution. We know that ammonia can act as a base and exhibits alkaline properties, but contains no hydroxide ions. How is this possible? In this lesson, we will learn about the Bronsted-Lowry theory of acids and bases, which fills in the gaps in the Arrhenius theory. You have learned that acids are substances with a pH lower than 7. We can test for acids using universal indicator solution, or paper, which turns red or orange, all depending on the strength of the acid. Blue litmus paper also turns red in the presence of an acid. An example of an acid that you are likely familiar with is hydrochloric acid. Hydrogen chloride dissolves in water to give hydrochloric acid. Hydrogen chloride will dissociate to give a proton and a chloride ion. The proton is not just released, but it is transferred to another substance. For our example, water accepts the proton to form a hydronium ion. A hydronium ion is also known as an oxonium ion. A Bronsted-Lowry acid is a substance that releases or donates protons in solution. In our case, hydrogen chloride. A Bronsted-Lowry base is a substance that accepts protons in solutions. In our case, water. Notice that the definition of a Bronsted-Lowry acid or base is not a function of pH. So an acid-base reaction, according to the Bronsted-Lowry theory, involves the transfer of a proton from one substance to another. In the introduction, we mentioned that ammonia acts as a base even though it does not release hydroxide ions, which is stipulated in the Arrhenius theory. When ammonia dissolves in water, it accepts a proton from water. Notice that this reaction also involves a proton transfer. Can you figure out which substance is acting as an acid in this example? Which is acting as a base? Please pause the lesson to think about this and resume when you are ready. In this example, water acts as a Bronsted-Lowry acid because it releases a proton. Ammonia acts as a Bronsted-Lowry base because it accepts a proton. So a base, according to the Bronsted-Lowry theory, does not need to have a pH greater than 7, or turn red litmus paper blue, or turn universal indicator solution or paper blue or purple. The only requirement is that it is able to accept protons. Have you noticed that water acted as a base in our first example, but as an acid in the second example? Substances that can act as either an acid or a base are amphoteric. In conclusion, According to the Bronsted-Lowry theory, an acid is a substance that dissociates to release or donate protons. A Bronsted-Lowry base is a substance that accepts protons. Therefore, an acid-base reaction, according to this theory, involves the transfer of a proton.
Alrighty, so hopefully that's clarified things a bit for you. We're going to dig a little bit into different properties of acids and bases now. So as we already said, acids we know are proton donators, or H plus hydrogen ion, sometimes called hydronium as well, but generally we just say actually proton donators. So acids are proton donators. They're corrosive, which means they react with solid substances and living tissue, and they'll essentially eat them away. And this is basically they chemically react with them and break them down and break those substances down. And we talk about this being corrosive. Particularly with really strong acids, you want to be careful about getting them on yourselves because you'll get a chemical burn where it starts to corrode and eat away at your skin. Acids, we tend to say, have a sour taste. In fact, this is actually where the word acid comes from. It comes from the Latin word for sour, which is acidus. So they noticed that there was this group of things that tasted sour, and so they named them acids. And it just so happens that they have a lot of other properties in common too, including what they do with protons. So acids have a sour taste. When we go through the examples, you'll see a number of common food examples in there, and yeah, they're quite sour as well. Acids will have hydrogen in them. Remember, they have to have hydrogen because that's what they're giving away. So they'll have hydrogen, but they'll have it in combination with other non-metal elements. So that could be chlorine, it could be sulfates, it could be a nitrate or carbonate, or it could be a phosphate, all these other groups with phosphorus and oxygen or something like that. So acids will also, when they're in solution, they will conduct electricity. And this is because they've got free moving charged particles, and therefore they are able to conduct electricity. So like we already said, they basically react by giving away their hydrogen as an H plus ion. Some examples that you're probably familiar with would be hydrochloric acid, a pretty common substance used in the lab. Sulfuric acid, again, something we use in chemistry, but it's also something that's in the common car, in your car batteries. Vinegar is properly known as acetic acid. So vinegar is also an acid. Lemon juice has citric acid. All citrus fruit will have citric acid in them. Lemons tend to have more of it. Apples actually have malic acid. So you've got a few food examples there, and they all tend to be quite sour ones as well. Why? Because acids have a sour taste. So that's acids. Bases, remember, they're the opposite. They don't donate their protons. They accept protons, or those hydrogen ions. Now, whilst acids can also be quite corrosive, we tend to say the word caustic for bases as opposed to corrosive. And they do a very similar thing. Bases can be very, very good at breaking down hair, fat, vegetable matter. In fact, this is why cleaning supplies are bases pretty much all the time. Unlike acids, they don't have a sour taste, rather they have a bitter taste. And we tend to think of them as having this slippery or soapy or slimy touch, which, given most of them as cleaning agents, that's the reason we tend to associate bases with having a soapy feeling, is because soap, which is a cleaning thing, is actually a base. When they're in solution, we actually call them alkalis. So base is when it's a sort of solid, and once we mix it in with water, we then call it an alkali. Basically what happens is bases neutralize acids by taking that hydrogen ion. So acids are giving the hydrogen ion or the proton away, and bases are taking it, and in doing that they neutralize each other. Some examples of bases we've got there are sodium hydroxide, bicarbonate of soda. We tend to just call this bicarb soda. It's something you probably have in your kitchen. Ammonia, soaps, bleach, all of these are bases. Now, how do we measure how acidic or how basic a substance is? Well, that's what we do here. We use the pH scale. pH, so we think of as standing for possibly potential hydrogen, but it's just a way of describing how acidic or how basic a compound is. If something scores from 0 to a bit less than 7 on that scale, it's considered acidic. If it scores from just above 7 all the way up to 14, anywhere in there, it's considered basic. And if it is specifically right on 7, we say it is neutral. That is our midpoint. It's neither an acid nor is it a base. And really, this is particularly using Arrhenius's definition. We look at the ratio of hydrogen plus ions to OH or hydroxide ions in solution. So you can see over here on the side, where we have a greater amount of H plus ions compared to the OH ions, it is acidic. All right, so substances with a greater concentration of H plus ions are acidic. If they have equal concentrations of H plus and OH minus, then we say that they are neutral. If, however, it's the other way around and they have much more OH negative ions than they do H plus ions, then we say they are basic, or they're in an alkaline solution. So that's sort of the technical aspect behind pH and how we actually work that out. So generally speaking though, substances need to be in a solution to find their pH, because we need to see how they're giving off those ions, and we see that best when they're in solution. You can actually use an indicator, which is another chemical, to work out what the pH of a substance is, because things don't always just come with a label on it, and you could be talking about one chemical, but depending on what you've done with it, maybe the pH has changed or something like that. And so to work out what the pH of the substance is, we use these chemicals called indicators to basically find or work out precisely what we're talking about. And we do that by looking at the color that those indicators turn. The really common one we use with acids and bases is universal indicator, and it has a full color spectrum that goes all the way from very, very acidic to very, very basic, and passes right through neutral as well. So it's really handy for getting a really good indication of, is it an acid, is it a base, is it neutral? Not all indicators have as big a range. Some of them are much more precise. And maybe they only show you if something's an acid or not. It doesn't actually let you know, maybe is a thing neutral. Just be like, this is an acid, and it'll change color on that, but it doesn't change color for anything else. So universal indicators are a really handy one. And you can sort of see in the diagram down the bottom, your acids are from the red through to orange and to be yellow. Neutral is sort of your green colors, and your alkali or bases are your blues through to purples. If you have a green colour and it's a bit yellow, then you're probably on the acidic side of neutral. If you have a green colour that's a bit bluey, you're probably on the basic side of neutral. So you can even look at things like that. It won't give you a precise number, but it'll give you a really clear range that your pH will be falling in for that solution. So we use indicators to identify the pH of solution, and we do this by looking at the colour that they are. All right, so I've got another video here just on the pH scale, so we're going to play that now.
In this video, we're going to have a look at the pH scale and some other simple indicators of acids and alkalis. In other videos, we have seen what makes something acidic, neutral, or alkaline. We can tell if something is acidic, alkaline, or neutral by using an indicator. Indicators are substances that show different colours when they are in acidic or alkaline conditions. Litmus paper is a simple indicator that tells us whether something is acid or alkali. Litmus is red in acids and blue in alkalis. Litmus paper is made from lichens, which have been used to dye cloth for hundreds of years. It can be used as a liquid or paper. The paper is easier and more reliable. It comes as red litmus paper and blue litmus paper. Red litmus paper changes colour from red to blue under alkaline conditions, but no change under acidic conditions. Blue litmus paper changes colour from blue to red under acidic conditions, but no change under alkaline conditions. So just remember that red litmus paper changes colour for alkalis, and blue litmus paper changes colour for acids. However, litmus paper only tells us whether something is acid or alkali, but it does not tell us how acidic or alkaline a substance is. For this, we have the pH scale and a universal indicator. Universal indicator is a mixture of different indicators, or dyes, which has many different colour changes, and so shows us the pH value of the solution. Again, it can be used as a liquid or a paper. The pH runs from 0 to 14, with 0 being extremely acidic, 7 being neutral, and 14 being extremely alkaline. Stomach acid is a strong acid with pH of about 2. Acid rain has a pH of about 5.5. Milk is neutral with a pH of 7. Seawater is a slightly alkaline. Soapy water is a strong alkaline. And bleach is a really strong alkaline with a pH of 13. Universal indicator is so called due to its ability to indicate the entire pH spectrum. There are other indicators that can be used that have other colour changes, but these two are the ones you need to know. We can also get even more accurate measurements of pH using a pH meter, which will give us readings to 0.01 of the pH. So from this lesson, you should now know indicators can tell us whether something is acidic or alkali and how acidic or alkali it is. Red litmus paper changes colour for alkalis, and blue litmus paper changes colour for acids. And universal indicator can give us more detail, indicating where on the 0 to 14 pH scale a solution is. Acids are from 0 to 6, neutral is 7, and alkalis are 8 to 14.
Alright, so another point I want to touch on before getting to neutralisation reactions is a bit of terminology. We often talk about acids and bases being strong or weak, and it's a strong acid or it's a strong base, or weak acid, weak base. But a lot of people get confused what this actually means. So strong and weak don't have to do with how concentrated it actually is. If you want to talk about how concentrated it is, it's sort of like you can have concentrated cordial versus dilute cordial. Then we use the words concentrated and dilute. It's just how many of molecules of that acid are in there or that base are in there versus how much, say, water. That's a different concept to strong and weak. If something is strong, if it's an acid or a base, then that means it's really good at getting rid of, for acids, the H plus ions, or bases, the OH ions. All right, so they'll have very low for acids or very high for bases, pHs. So these are things that are very, very good at putting those ions out there and creating them, and they have the pHs at the extremes of the scale. If something is a weak acid or a weak base, it actually isn't as good at releasing those H plus or those OH minus ions. And so you're going to see a pH, if it's an acid, below 7, but it may not be very far below 7. And if it's a base, it'll be above 7, but it may not be very far above 7. So the technical term is we'd say, talk about how well they dissociate and that sort of thing in solution. And this just means how well they separate. And you'll find that acids and bases that are strong do this very well. And when they're weak, they don't do it very well. That sort of thing. And this is why some acids can cause a lot more damage than others. For example, vinegar tends to be a pretty weak acid, whereas something like hydrochloric acid tends to be a very strong acid. So you have to be careful with them depending on different things. So here are some actual examples of them. So you can see that acids, hydrochloric, nitric, hydroiodic, perchloric, and chloric acid are all strong acids, but sulfurous, methanoic, phosphoric, nitrous, and hydrofluoric acid are maybe not as much. And on the base side, lithium hydroxide, sodium phosphate, calcium hydroxide, barium hydroxide, sodium hydroxide are all considered strong bases. But your ammonium hydroxide, sodium carbonate, ammonia, potassium carbonate, zinc hydroxide, not as strong a bases, and that sort of thing. So that's a bit of background on acids and bases. Now let's talk about what happens when you react them together. So when you react an acid and base together, it is a neutralization reaction. And the reason for this is they completely counteract each other on an atomic level, and they end up bringing that pH towards 7 or towards neutral, hence they're being neutralized. Now, depending on how strong the acid or the base that you add is and how concentrated it is as well, and how much of it you add is going to dictate whether or not you actually get to 7. Okay, you might end up, if you have an acid and you add some base, you might end up going towards 7, but you may not actually quite get there. Or you might completely go past 7 and end up more on the basic side. Depending on what you combine, there's a whole range of different things. But when you do have an acid and base come together and they react, they follow the same pattern. Acid plus base gives water plus a salt. Now, salt here is a general term meaning any ionic compound made through an acid-base reaction. Often we talk about salt being table salt, and that's sodium chloride. That is just one example. Okay, you can have a lot of different salts made through acid-base reactions. We'll actually look at that in a couple of slides, and we'll look at how you can even work out what its name will be. So acid plus base gives water plus a salt. That will always happen. If you add too much base to an acid, then you'll have excess base left over, and so your solution, even though this has happened, will be more basic, and so you won't actually have a perfect neutral pH, but you will have had this reaction occur. So basically what we're saying is that when this reaction happens, your pH will head towards 7, but for different reasons, it may not actually reach it. But what you know happens is that you will produce some water and you'll produce some type of salt. Now, if you actually have a base that has the word carbonate in it, then you are also going to produce carbon dioxide. And so you can see there's a second reaction down the bottom there. It says acid plus base, when that base is a metal carbonate, is going to give you the salt, water plus carbon dioxide. And so those reactions down the bottom are ones where you'll definitely see fizzing or bubbling and that sort of thing. If you ever added vinegar and bicarb soda together at home, you've seen this, because vinegar is acetic acid and bicarbonate soda, well, that's a carbonate of, it's a metal carbonate. So you're going to have this reaction happening. You're going to produce the salt, water, and carbon dioxide. And you get lots of bubbling, and you've got to contain it in the sink. Otherwise, your mum will get mad because you've made a mess. All right. So let's talk about those salts we can make. Different acids and bases are going to produce different salts. Now, the salt gets named based on what they're made from. Okay, so you can see a bit of a table there. It says acid plus base gives water and salt. And the second row says hydrochloric as your acid plus sodium hydroxide as your base is going to give you water plus NaCl or sodium chloride as your salt. Whereas if we started with nitric acid, which is HNO3, and we added it to potassium hydroxide, which is KOH, it's going to give us water, but it's going to give us potassium nitrate, KNO3, as the salt. So the way you work out what the salt produced is by taking two terms, one from the acid, one from the base. So you need to take the name of the positive metal ion, or ammonium, if it is an ammonium. You need to take the name of the positive metal ion, and you need to join it with the negative ion of the acid. So your salt name will be the metal or ammonium from the base plus the negative ion from the acid. Okay, what this means, take lithium hydroxide. Okay, lithium hydroxide is a base, the metal in it is lithium. So we're going to take lithium as our first word. So we're going to react it with sulfuric acid. So you've got a table down here, and it says if it says sulfuric, the negative ion is sulfate. So that's going to mean you're going to get lithium sulfate. Okay, and that's what we've got over here. So there's some examples in these tables down below. You've got a list here of the different types of acids and what the negative ion name is that's in that. So hydrochloric is chloride, sulfuric is sulfate, nitric is nitrate, carbonic is carbonate, phosphoric is phosphate. Those ones are a little harder to identify than the metals. The metals tend to be, sodium hydroxide, the metal is sodium. Okay. If you see ammonia as your base, just put the word ammonium in instead for the metal, because it obviously doesn't have a metal as part of it. It's a bit of an odd base that we've got there. So I want you to give this a go now. Here are some acids and some bases. Use the stuff on the page before to work out what the salt's going to be produced are. So I'm going to pause the video and give that a go. Alrighty, let's go through the answers now. So we'll start off with sulfuric acid. So this is sulfuric acid, and we've got sodium oxide. So if we react these together, the metal name here is sodium. So we're going to go sodium. And if you look on the page before, it says when it says sulfuric, the negative ion is sulfate. So this is going to be sodium sulfate. All right, so that's the first one. Second one, we've got hydrochloric, so we're interested in that chloric bit, and calcium hydroxide. So calcium is our metal, CalCium, calcium, and hydrochloric, table 4 tells us that we need to use chloride. There you go. All right, number 3, we'll quickly look over here. Our metal is copper, so we'll pop that in. And nitric acid, if you look on the table before, nitric means it has a nitrate. All right, number 4, potassium is our metal. And phosphoric gives us phosphate for the negative ion. Okay, lucky last. Looking here, magnesium is our metal. And carbonic, if we look on the table before, carbonic means that that acid has a carbonate group. So we're going to write carbonate. Okay, and there we go. So you can see our salts would have been sodium sulfate, calcium chloride, copper nitrate, potassium phosphate, and magnesium carbonate. So that is how you name a salt. All right, hopefully you went okay with that. Remember, if you didn't get anything, you can rewatch this video, you can speed it up, slow it down, just watch the bits you need to watch, or you can always go and ask your teacher if you need any help or have any questions on the stuff gone through in this video. Anyway, that's all for today. Thanks for watching, and enjoy that little joke.